In lesson 4.3, we're going to talk about the triangle inequality idea. And it says that the sum of the lengths of any two sides in the triangle has to be greater than the third side length. If this is not the case, then either the sides form a line or fall short of each other. So in the first example, on the top left, what we see in this particular triangle right here is that if we take any of the two sides, for example, AC and CB, and we add them up, 1.8 plus 2.2, that gives me a grand total of 4, which is indeed greater than the third side, 3. It doesn't matter which two I add, any situation I pick out of that triangle should be the case where if you add 2 up, it's bigger than the third one. Moving to the right, I can see that if I take the same two sides, 1.5 and 2, that's 3.5, that's still bigger than the third side. Bottom left, if I take the top two sides, 1.3 and 1.8, that's greater than 3, it's 3.1. But on the far right side, if I add those two together, the 1.25 and the 1.75, that equals exactly 3. You have not formed a triangle here, you've just laid another line, so to speak, on top of the first line, AB, because the two sides fall together and, in that case, don't form a triangle. As one final example, what I could have done is, let's say I make the bottom length AB, that's still that same 3 that we had before, and then I take a side, and AC is a 1, let's say, and I could make BC, which we think is BC, but it's not really BC, and I tell you that that side length is 1. And now, when these things fall down to meet, not only do they not form a triangle, but they don't even touch each other, they're way short. Again, showing us that you have to have the two sides add up to more than the third side to even make a triangle. Something that's kind of neat about triangles is things are relative. So in triangles, the small side will always be across from the small angle. The medium side will always be across from the medium angle, and the large side will always be across from the large angle. If we look to the right, we can see this same scenario with numbers involved. Notice that the small side is 50 and the smallest angle is 10. They're across from each other, far away. The medium angle is 75 and the medium side is 60. And finally, the large side is 70 and the large angle is 95. The actual numbers themselves don't matter, just the relative sizes matter. Small is across from small, medium is across from medium, large is across from large. In our last slide in this lesson, we're going to talk about exterior angles. So there is a theorem that says that the exterior angle of a triangle is equal to the sum of the two remote interior angles. So as I look at a side of a triangle, let's say I'm looking at the bottom side of this triangle, I notice that there is an angle that's on the outside of the triangle formed with the side and the extension of the base. That angle, the exterior angle that we're looking at, is equal to both of the remote interiors. Now the word remote means far away from, like a desert island kind of thing. So notice that when I highlight the exterior angle in green, I'm not talking about the angle that's right next to it that I just put the X for. I'm talking about the two angles that are farthest away. And so to kind of show you how this works with numbers, if I look at the exterior angle on the right-hand triangle, which is 135 total, what we're saying is that 135 there is equal to the 93 plus the 42. So the sum of those two yellow highlighted angles, the remote interiors, is equal to the green highlighted angle, which is called the exterior angle. And the one that I didn't want was the one that was right next to the exterior angle, which was the 45-degree angle. That 45-degree angle is accurate in its measurement, but it's not the two remote interiors. So this slide is saying that the exterior angle of a triangle is equal to the sum, or in other words, the addition of the two remote interior angles. Down below, that's written down, 93, 42 are the two remotes, and 135 is the exterior.